particular talk, we're gonna try to have a more general abstraction of the problem formulation. So we're gonna focus on solving the large-scale sparse nonlinear optimization problems and how do we accelerate the solution process on the GPU. So I'll talk a little bit about the algorithm, but of course, I will also talk a lot about the software implementation because our main motivation for this study is coming from porting the existing algorithm on the GPU so that we can exploit this relatively new hardware. Okay. So yeah, a little bit of introduction of myself. I think Shangli gave a really good overview. But now I recently joined the MIT just 2 years ago, and then this is my research group, and we have been focusing on, of course, one topic is the GPU-based optimization, but we are also trying to expand the scope of the application to different application domain, including the control problems, chemical process design, and so on. And for today's work, I'm going to be focusing on more of the methodology side. And then for this part of the work, the main contributors are these 4 people. So this is Alexis Montoisen, Francois Paco, who is at Mines Paris. Alexis is now with AMD, and Mihai Aintescu, who are the postdoc boss of all 3 of us. So this kind of stems from partially overlapping 3 postdocs, and then we have been developing these algorithms and solvers. And now we are seeing quite a lot of contributions to our open source package. And these are the contributors to our main solver, MadNLP.jl. And then that focuses on the nonlinear optimization problems. But now we have the people who are working on different algorithms like the augmented Lagrange method, the interpointing method for linear optimization problems, and the complementary problems. And then there are a few people are working on different spin-off of the solvers. Okay, so the problem that we are targeting are the large-scale nonlinear optimization problem. And for this domain, I believe one of the most important application is how do we operate and optimize the operation of the power grid. And then recently, our tool has been utilizing this NVIDIA-developed direct linear solver. And in nonlinear optimization, oftentimes most of the computation is actually performed by within the direct linear solvers. And we were able to successfully integrate this solver into our nonlinear optimization framework, and we were able to achieve quite significant speed up. And then this is something that we are considering as the really getting mature technology that can be also used for the practical operation of the power systems. So the current state of the art of the solver, just to give a high-level overview of what this can do, I'll try to share. Let me just try to open the quick demo. Here. Yeah, so in this demo, on the left-hand side, we are solving the largest instance of the AC optimal power flow problem. This is the operation problem for the power grid. And on the left-hand side, we have the conventional state-of-the-art solver, open source solver IPOPT. And on the right-hand side, we have our implementation, MadNLP.jl. And you can see that you can solve the problem a lot faster. And if you just compare the raw computation speed, if you only count the real-time online computation part, it's about 40 times faster than the state-of-the-art CPU server. So this brings quite significant benefit in terms of the computation speed. And then today I'm going to be talking specifically about how we were able to enable this significant speed up for solving these problems. Okay, so now I'll get into more of the technical discussion. So GPU, and by the way, if you have any question during the presentation, feel free to unmute yourself and interrupt and ask questions. That's fine for me. So GPU, of course, it was originally developed for solving the graphics problem, and then that's where the name is originating from. It is the many core accelerator with the high memory bandwidth. It is used for graphics, but nowadays it is more often used for ML and AI workflows. Essentially, it is really good at performing repetitive computation by using the parallel computing resources. So it is really good at performing the matrix multiplication, and most of the time is spent for the matrix multiplication if you think about the large AI model training. So this is most nowadays what GPU is mostly used for. But if you think about the classical algorithms, and what I mean by classical optimization is the mathematical programming problems, not just the machine learning training. those algorithms has been considered to be less suitable for the GPU acceleration. And the state-of-the-art solvers on the CPU relies mostly on the sparse linear algebra operations. And these can be things like sparse matrix vector multiplication or sparse factorization of the matrix for solving the AX equals to B. And those computing patterns are quite different from the general dense matrix multiplication. So there's no like very straightforward way of porting that algorithm on the GPU. So if you go into the low level computational kernels to implement the optimizing algorithms, you can see that many of the kernels are missing there. So you cannot just directly port the algorithm over to the GPU. And that's kind of the main concern. But this status quo has been the case for many years, but recently this has been the landscape is changing quite rapidly, and that's going to be the focus of this talk. So when people talk about the GPU acceleration for the classical optimization problems, they may include things like linear, quadratic, and the nonlinear optimization. People have been mostly focusing on this so-called factorization-free method for solving these problems. And one of the most notable success was the PDLP algorithm. And this is something that the commercial solvers and open source solvers are actively integrating in the past few years. And this is the first order variant of solving the linear optimization problems. So you essentially do the first order primal update and the dual update, and we just iterate over them. And then, of course, there are a lot of other heuristics that is necessary in order to stabilize the behavior of the algorithm. And PDLP algorithm has achieved quite a lot of success. And before that, like there are some of the attempts to utilize some of the factorization-free methods. And those include using the iterative linear algebra within some optimization algorithm. In particular, you can use the projected conjugate gradient within the ADMM method in order to avoid the use of the matrix factorization and just perform the sparse matrix vector multiplication based implementation of the solver. And that has been possible in the past. And then before that, like for the nonlinear optimization problems, you need to combine a large number of different algorithms, augmented Lagrangian method, interpoint method, and inside of that, like when you're solving the KKT system, you can use the PCG algorithm, and that has been proposed in the past. But among these, the most notable success was the PDLP algorithm applied to the linear optimization problems. And now people are working on the generalization of this method to more general class of the convex optimization problems. And the key benefits of these variant of the algorithms is that they can solely be implemented based on the GPU-friendly kernels. And if you think about sparse matrix vector multiplication and adding and scaling one vector and adding or subtracting to another, map, which is just applying the same sort of the operation to each of the entry of the array and reducing after that, like these are kind of the very, very widely and flexible kernel that can be used for implementing the solver. And for these kernels, they're arguably very parallelizable, because if you think about the sparse matrix vector multiplication, if you parallelize by each of the row for doing the operation, you can still like exploit the parallelism pretty well. So for these sort of the kernels, there's a very straightforward way to implement it on the GPU, and then there are very like mature kernel that is already developed for you. So you can still rely on these kernels and then implement the algorithm based on that. And then these factorization-free methods can only be relying on these a few number of kernels. And once they are implemented, because they avoid the use of the matrix factorization, they can be scaled to extremely large-scale problems. Well, of course, the limitation of these methods is that they're mostly based on the first-order method, and sometimes, if under some nice regularity conditions, they can linearly converge, or oftentimes they sublinearly converge. So the main challenge there is that obtaining the high-precision solution is quite difficult. And then if you want to obtain, for example, 10 to the minus 8 accuracy, which is quite common in the double precision solver, that tends to be more difficult than using the second order methods. So in this context, what we are interested in doing is to implement the solver still based on the second order classical algorithms, but we want to utilize, and we also want to utilize the direct linear algebra. But that tends to be a little bit more difficult, and then I'll get to the practical challenges there. So the problem that we're considering in this talk is the large-scale, sparse, and constrained nonlinear optimization problems. In the generic form, you can state the problem in this way. You may have the variable bounds, inequality constraints, and some of the G flat and G sharp might be the same. In that case, that's going to be the equality constraint. And we have the objective function. But for simplicity, we're going to simplify the problem formulation a little bit, but we can do this conversion without the loss of generality, and then you can state the problem in this form. We're minimizing fx subject to gx greater than or equal to 0. We'll particularly focus on the class of the problem that has the twice continuous differentiability, and this is the requirement for applying the second order most of the second order algorithms. And generally speaking, we consider the non-convex objective function and the constraints. So that will make the problem non-convex optimization problem, but we will only seek for the local solutions. And then we are not going after the global optimization problems. And the potential problem of interest, for example, the power grid operation problem, you need to consider each of the line, bus, the generators, and so on. And that tends to be like pretty large scale optimization problem. For the large instances, we may have millions of the variables and constraints. But whenever you talk about large-scale optimization, almost always you assume that there's some sparsity that we can exploit, and that's the case for the problem of interest. So we are considering the problem where the constraint Jacobian, the Jacobian matrix for the constraint function, or the Lagrangian Hessian, and those are going to be the symmetric matrix, and those are the sparse matrices. So our strategy here, the way that we're going to attack this problem is that we're going to design the algorithm that exploit this sparsity so that we can scale up to very large scale problems. And most of the existing solvers are actually designed based on this abstraction. So we consider some smooth optimization problem, but we always assume that the constraint Jacobian and the Lagrangian Hessian are sparse, so we can design the direct linear algebra solution method in such a way that they can exploit this pattern. And most of the interesting instances, for example, the energy system domain problem that I mentioned before, they fall into this category. And for optimal control problem, of course, there are more domain-specific structure. But if you want to formulate the problem in this standard nonlinear optimization form, that will fall into this category. And the sparsity there is coming from the temporal coupling structure. And if you think about nonlinear optimization problems, the way that I think about this approach is that this is most useful in order to guarantee the feasibility under the nonlinear governing equations. So for nonlinear optimization problems, you may have a much weaker guarantee compared to the convex optimization. For example, if you think about the convex solver or the LP or the QP solvers, you can see that they can converge very robustly to the solution. That's the distinct nature of the convex optimization and the key benefits. But for the nonlinear optimization, sometimes the solver fails, and then that's kind of expected. And if you look at the global convergence result of nonlinear optimization algorithms, you can see that they rely quite a lot on the property of the problem. So the solver can always fail, but remarkably still, the solver performs quite robustly. But in terms of the guarantee to the solution, probably you may expect the weaker guarantee, and that's kind of the general characteristics of the nonlinear optimization solvers. But the key benefit of that is coming from the fact that you can directly embed the rigorous physics-based model, the governing equation of the system. And in that way, you can embed things like the powerful equations. If you will, you can embed the dynamical equation for the chemical kinetics, discretize partial differential equations, and dynamics of whatever system that you are interested in. And that's the key benefit of nonlinear optimization. And then in that way, you can ensure the feasibility under the nonlinear governing equation. And that's where the nonlinear optimization is most useful, and this can be used for solving those problems. And another key highlight of the capabilities of the nonlinear optimization solver is that the solution of this can always guarantee the nonlinear feasibility, and then they can be used for improving the potentially the linearized decision-making practice that has been used in different domain. So DC optimal power flow is kind of the standard algorithm for clearing the energy market. But if you convert to the AC optimal power flow problems, then in that way you can embed the physical governing equations such as the nonlinear power flow equations, and that can give you some of the benefits in terms of being able to find the solution in a more rigorous fashion. And now I'm going to be talking about the decomposition of the nonlinear optimization software stack. And this will apply both for the CPU and the GPU. And just as a broad classification, it can be decomposed into algebraic modeling system, which provides the interface to the user and the capabilities to evaluate the sensitivity of the model functions. And the second is, of course, the nonlinear optimization solver, which orchestrates the overall procedure. And the third is the sparse direct linear solver. So this is the breakdown of the solution time for solving the problems on CPU or the GPU. So you can see that quite significant time is spent for the direct linear solver, and that's always the case for the CPU or the GPU. And another chunk of the time is spent for AD or the automatic differentiation. And this is the part where you evaluate the function for the given objective and the constraint. You may need to query for the given point, what is the objective value, what are the constraints. And then you also need to evaluate the derivative of this information. And then our goal is to apply the second order derivative. And that requires the computation of the gradient, Jacobian, and Hessian. So that portion is marked as the red. And internal is what's used within the solver, and you can see that the solver itself doesn't spend much time in the computation. So most of the computation is actually delegated to the automatic differentiation engine or the sparse linear solver. And the other part is the initialization. And most of the part is used for doing the symbolic analysis of the sparse linear systems. And the construction is the model construction that is used for interacting with the user. So in terms of the online computation, the last three portion is the important ones. So if you're, for example, deploying this to the real-time operation, you typically can reuse the symbolic vectorization over and over, and then you don't need to reconstruct the model. So the real computation part is the last three part of this on this graph. Okay, so the algebraic modeling system is the part that the software stack interact with the user. So like these are typically implemented as the nice user interface that include jump, ample, and Kasadi, and especially for the control community, I think Kasadi is getting a lot of love. And this is the part where you specify this is my objective function constraint, and this will give the software the full details of the algebraic expression for the objective function and the constraint. And based on that, they can automatically construct the so-called callback function that can be queried by the solver. There will be the callback function for the objective, constraint, gradient, and so on. And based on this information, the solver can put together this so-called KKT system. So I'm not going to try to give you the full overview of the nonlinear optimization algorithm, but when you're applying the second order method, that means at some point you're solving the step computation, the Newton, the KKT system that essentially try to compute the Newton step direction from the given specified point. And for computing the Newton step, on the left-hand side, you will have the second order derivative of your Lagrangian Hessian. And on the right-hand side, you will have the first order derivative. And by using this callback function, you can essentially construct this KKT system. On the left-hand side, you can see that there's the Lagrangian Hessian, the constraint Jacobian, those information is located over here. And there are a few additional terms that may be coming from the regularization of the problem or the terms that is arising from the barrier problem. So if you're doing the interpolate method, you are replacing your inequality constraint with the smooth log barrier function, and you want to also differentiate that part. And those terms will appearing over here. And on the right hand side, we will have the first order derivatives of everything. So yeah, this is the standard so-called KKT system, and you need to compute the step direction by solving this linear system. And as you have seen before, like the significant portion of the computation time is spent for computing this step direction. And sparse direct solver needs to be used for solving this system, and that's because if you try to use the iterative method, oftentimes the solver just fails, and that's because we're doing this within the interpoint method. And then the way that interpoint method handles the inequality is that we are going to approximate the constraint by using the smooth log barrier function. And if you reduce that barrier parameter, at some point, this will be almost a non-smooth function. And meaning that if you evaluate the Hessian information at that boundary point, then that will lead to very serious ill conditioning in the KKT system. So this specific entry that can reach up to 10 to the 10, 10 to the 12 in the double precision implementation. And that's almost as large. If you think about the condition number, it is as almost large as the inverse of the motion precision. And if you get into that regime, ensuring the numerical stability is now really a non-trivial problem. And then with the iterative methods, typically you cannot solve the system reliably. So you need to use some sort of the direct linear algebra method. So on the CPU, the standard implementation are the MA27, Paradiso, and so on. So now we want to port this all software step onto the GPU. And now we're going to discuss whether this is going to be even possible at all. So porting the AD, automatic differentiation, is like relatively straightforward. But if you just want to accelerate one procedure, then typically that's not sufficient. Actually, you need to port all different components of the algorithm on the GPU. And the reason is that on the CPU and GPU, the different memory is used, and the interface between the CPU and the GPU tends to be pretty slow, meaning that if you want to only port AD or only sparse linear algebra on the GPU, then you need to pay this high penalty, which is caused by the overhead between the communication between CPU and the GPU. So you don't want to do that. So if you want to go for the GPU implementation, you want to port everything over to the GPU, and that's basically where most of the challenge is coming from. So doing the AD is relatively straightforward. So we have implemented the GPU-specific algebraic modeling system. You can kind of think of this as a Kasadi for a GPU-based nonlinear optimization, and we have that implementation ready. But for porting the direct linear solver is very non-trivial work, and there's no drop-in replacement for MA27. So we need to find some way to adapt the interior point method for the GPU so that we can utilize relatively less capable direct linear solver. So I'll try to elaborate what I mean by that. So on the CPU, what happens in the direct linear solver is that you are trying to factorize this KKT system into this PQ LBLT Q transpose P transpose form. So we're essentially factorizing matrix with the series of the matrix multiplications. And here, P is the reordering of the matrix. And then for any of the sparse linear algebra operation, this is necessary to ensure that the fill-in, the non-zero entries after the factorization is minimized. So this is essentially quite critical for ensuring the scalability by utilizing this sparsity of the problem. So but nice thing about this is that this can be computed only once, and the sparsity pattern typically doesn't change over the iterations. So you can reuse this across IPM iterations. So you need to pay some price, but this is typically tolerable for many of the applications. But the real difficulty is coming from the numerical pivoting, and this is necessary in order to ensure the numerical stability of this matrix factorization. And as I mentioned before, for GPU solvers, we are really going after very large-scale optimization. And when you are factorizing very large metrics with millions of the entries, you can always get into the situation that you have to divide something by some number that is very close to zero. And if that happens, then it will break the numerical stability of the overall implementation. So you want to avoid that. And the standard technique, or if you have taken the numerical linear algebra course, you might have heard about this technique, numerical pivoting. And that's essentially switching the order of the elimination on the fly in order to avoid the situation of having to divide something by something very close to zero. And we can perform this operation, and then this is something that we do simultaneously along with the LBLT factorization. And then LBLT factorization is essentially decomposing the matrix into the lower triangular, block diagonal, and the upper triangular formulation. And B here is the 1x1 or the 2x2 matrix. So this is relatively easy to solve. Lower triangular, that's also easy to solve. And Q and P are just the permutation. So once you have factorized the matrix in this series of the matrix, then now there's the clear way to how to solve the system for the given right-hand side. So this is kind of the standard procedure on the CPU to solve the KKT system. But the main pain point is the numerical pivoting. And that's because you need to switch the order of the elimination on the fly during the factorization process. And for the parallel computing, this is really kind of the very difficult things to implement. So people have been recognizing that like this numerical pivoting has been the major difficulty in implementing the sparse direct linear solver. And if you need to do the numerical pivoting, that will break the sparsity of the parallelizable operation that you have analyzed all the way before, and that breaks the nice parallelizable structure like the uniform memory access, and it can potentially destroy the parallelism in the solver. So you want to avoid the use of the numerical pivoting, and many of the existing GPU solvers don't have the adequately reliable pivoting strategies implemented there. So that's kind of the limitation of the current state-of-the-art GPU solvers. So if you try to use QTSS with the vanilla inter-point method, such as IPM, such as the IPOPT, then you actually encounter quite frequent failure, and you almost always run into the numerical failure if you are dealing with the problem with more than 10,000 variables. And that was some of the anecdotal experience from our side. So the failure mechanism there is that the linear solver relies on the pivot perturbation, which is like a non-ideal situation that you can get into during the direct linear algebra procedure. And this is the procedure where you perturb the pivot, which is changing the pivot entry that you need to divide by. And then by doing that, you're converting you're making some of the changes in the original metrics so that you can factorize them better. But the factorization is going to be less useful because you're not solving the original system. So what's going to happen there is that you need to rely on this pivot perturbation, and then that leads to poor factorization accuracy. And then you need to rely more on the iterative refinement within the solver, and you're forced to do the primal dual regularization, and that leads to the slow convergence behavior. So you cannot just directly use the direct linear solver available on the GPU and then plug it to the existing IPM solver. So the strategy that we have developed, this is really the class of the algorithm that we call pivoting-free IPM. And in this pivoting-free IPM class of the algorithms, the approach that we've been mostly taking was converting the KKT system into some form that we can factorize without the use of the numerical pivoting. And you can do that if you can convert the system into a symmetric quasi-definite system or the symmetric positive definite system. And we're going to be particularly focusing on the latter case. And when the pivoting is required, the GPU solvers can very efficiently factorize the system. For the sparse positive definite system in particular, the QTSS solver has been quite successfully solving the large-scale positive definite system. So now our goal is to reformulate the KKT system in such a way that it can be converted into sparse symmetric positive definite or the quasi-definite system so that we can better utilize the GPU solver. So how can we do that? So the main reason that we have to deal with the indefinite system comes from the presence of the equality constraint. But if you can slightly relax the equality constraint, then actually you can treat everything as the almost an inequality constraint. The way that we do is that we introduce the slack variable. We still have the equality, but we are going to relax this slack variable to be slightly violating the constraint. So this tau parameter can be set as the same value as the solver tolerance. So if your solver tolerance is 10 to the minus 4, this is going to be the same as that tolerance. And if it's 10 to the minus 8, this is going to be matching with that. And then after this transformation, you can look at the KKT system. And now because of this presence, actually you can see that the lower triangular part of the KKT system becomes structurally non-singular. And this delta I and this I are the identity metrics, and S inverse sigma, this is just coming from the second order derivative of the barrier function. And because we have converted every equality constraint into inequalities, actually we have this structure. And once we have this structure, we can try to analytically eliminate those 2x2 blocks, and you can derive this condensed form KKT system. And in this condensed form KKT system, you can ensure that these metrics, even if you're solving the non-convex problem, after certain regularization, there is necessary anyway for ensuring the descent direction with respect to the merit function. Actually, you can ensure that this is the symmetric positive definite system. And this is something that we have wanted in the previous slide. And if you have the symmetric positive definite system, you can solve the problem effectively on the GPU by using the existing implementation of the solvers. So with this method, we can enable the numerically stable factorization of the KKT system without the use of the numerical pivoting. So that was the kind of the nutshell of the algorithm, and now I'm going to show you some of the numerical results of using these solvers to solve the large-scale optimization problems. So we try to first demonstrate this algorithm by using for the power system operation problem, the AC optimal power flow problems, and we have benchmarked the solver performance and then compare that against the state-of-the-art CPU implementation, IPOPT. And we have tested the solver performance for different level of the tolerance, 10 to the minus 4, 10 to the minus 8. And we have classified the problem into small, medium, and large problems. So each of these include multiple instances, but we are reporting the shifted geometric mean time, which is kind of the standard metric that is used for solver benchmarking. So this is essentially taking the geometric mean of multiple instances that is considered in the same bucket. For 10 to the minus 4 tolerance, MadNLP solver were able to solve the problem almost the same speed for the small problem. For the medium-sized problem, about 2 times faster, but large enough problem you can achieve like more than 10 times speed up, as you can see from this plot. So for the entire over the entire data set, you can see that MadNLP can achieve quite significant speed ups. And you can see that like it kind of makes sense that the speed up is limited for the small scale instances because there's not much room for the not much opportunity for the parallelism. But if you get into the large scale problems, there are more opportunities for the parallelism, and then you can achieve quite significant speed up there. But if you tighten the solver tolerance, actually you can see that the solver performance kind of degrades, and then you can see that some of the solver, for some of the instances, the solver is failing. And the key reason for that is that I'm gonna get to that a little bit of the detail later. But the KKT system that we need to handle, because we are doing the condensed formulation, actually that will increase the condition number of the KKT system. That means it's more likely that we may get into some of the numerical instability issue. And because of that, we are seeing some of the degradation in the solver robustness. So as of now, GPU can significantly accelerate the convergence of the algorithm, but at the same time, there is some of the trade-off in terms of the numerical stability, overall stability of the solver. So this is another instance. So this is a bit nicer problem. A lot of the problems in this COPS benchmark are the optimal control problems. But for this class of the problems, we could see that the parallelization is more effective and the GPU solver can achieve even more than 10 times speed up. Yeah, and the previous one was only one option for implementing the pivoting-free interpoint method, and there are actually a large number of different alternative implementation for the pivoting-free nonlinear optimizing solver. So this pivoting-free is kind of one abstract requirement that you need to pass in order to be better utilizing the parallel computing resources, especially on the GPU hardware. And in this alternative implementation, I'm gonna just give you the high-level overview. Again, the equality constraint is causing the indefiniteness of the KKT system. But what you can do is without changing the solution, you can add this Jacobian regularization by using the Jacobian transpose Jacobian block on the 1-1 block of the KKT system. And in that way, you can factorize this system without the use of the numerical pivoting. And then you can try to solve the short complement system without explicitly forming this, but you can utilize the direct factorization of the block that you see on the middle. And then if you apply strong enough regularization here, then actually you can ensure that the short complement approaches to the identity matrix as you increase this row. That means if you do the conjugate gradient like algorithm over this short complement, you can just make it converge in just a few iteration steps. And that way you can get the step direction, and then you can utilize that within the optimization algorithm as the step computation method. So this is another method that we have implemented, but these are not the only way, and we are also currently exploring a number of different directions. So our next goal is to, because we have kind of demonstrated this is in principle possible, but like we are trying to stabilize the behavior of the solver as the next step. Xiongling, how much time do I have left now?
6, 7 minutes.
6, 7 minutes. Okay, yeah, that's good. So, so something that we are quite interested as the next step is the batch optimization. So what I mean by batch optimization is that oftentimes we are interested in solving not just one problem. Actually, we want to solve an ensemble of multiple instances of the problems that can be coming from the optimal control problem. So if you, for example, are a robotics person, you might be interested in solving the contact problem. And depending on the contact, like different model might need to be used within the nonlinear optimization. In that case, you might want to enumerate multiple different options and then solve the problem simultaneously. So for that kind of use cases, like you want to develop a solver that can solve multiple instances simultaneously by using the parallel computing resources. In the energy system, there's a relevant use case, and that's essentially ensuring the feasibility of the grid expansion planning. So you decide to make the decision of like where to install the new generator, where to install the new transmission line, and after that you want to verify the feasibility of the operation over a large number of scenarios. In that case, you might want to parallelize over multiple instances. And this type of the problem have the key characteristics that you are solving kind of similar looking problems. So in terms of the problem algebraic structure and the sparsity pattern, they are all shared and they are the same, but they have the different numerical values used within the optimization problems. So for these problems, the batch optimization can be a useful workflow for enabling these parallelized computations. So so far, like we have the solver implementation, but we didn't have these batch optimization capabilities. But like, there was very recent exciting work by Michael Klemkin on Georgia Tech, who has been using our MadNLP solver for the batch linear optimization solvers. So like the slide is courtesy of Michael that I'm sharing today. Okay, so the key idea here is that we want to exploit the uniform batch structure within the cuDSS. What I mean by uniform batch here is that we have a large number of linear systems that has exactly the same sparsity pattern. And if you think about the problem that I described before, like those can be expressed as the problem with the uniform sparsity pattern. And for this problem, now you can form the KKT system, and then like this can be used within the batch solver to be able to accelerate the solution procedure for the linear system. And the key idea here is that when you're solving a large number of problems, not all of the solvers will be terminated in exactly the same number of iteration count. So some of the solvers may need to take more iteration, and some of the solvers may need to terminate early. So the key software engineering behind this is that you want to evaluate whether the solver is terminated, and then you want to reinitialize the next instance for some of the solver, and then for the other solver, they continue the iteration. So based on his implementation, now we can solve the problem, and then like you can see the decomposition of the what MadNLP is doing inside. Like factorization is taking quite significant portion, and there's the triangular solve, and then some internal time is used for within the solver, and then you can see that you can almost fully utilize the GPU computing resources, and there's not much of the time spent for just waiting. So this is our current implementation, and then like this has been utilizing this batch solution feature for the cuDSS, and then we have eliminated quite a large number of latencies there, and then like this is the result. And then if you compare the batch solution time compared to the CPU implementation or the GPU implementation without batching, that means just we're parallelizing multiple instances at the CPU level and then executing multiple jobs within the GPU, and then it can achieve quite significant speed up. So this is our current state of the art in terms of the batch implementation, and it has been implemented on the linear optimization problems. But now we're interested in generalizing this further to the nonlinear optimization problems as well. So now in this context, we can think about some interesting future directions. And then like for this class of the problem, the interesting question is whether we can do the same thing for the nonlinear optimization. And then this is like still quite a non-trivial question to us because for the nonlinear optimization, there can be some of the divergence of the algorithm, which cannot be efficiently handled by the batch solver. That's something that we are currently interested in exploring. And how does the dollar per instance cost change with respect to the problem size and the batch size? So for this instance, the metric is not just the solution time for solving one instance. Actually, we want to solve multiple instances. And for doing that, how should we balance the utilization of the GPU and then what is the kind of optimal sizing of the problem to enable the highest throughput of the GPU? And can this be applied to the real world problems? So I think I mentioned a few applications for the control and the energy system context, and we are interested in exploring those ideas. And how can we remove the heavy tail in the runtime distribution is something that that kind of the big challenge for us. So as I mentioned before, if you tighten the tolerance, the GPU solver's convergence is not as reliable as the CPU solver, and that means if you see the runtime distribution of the multiple instances, there can be quite heavy tail, which takes a large number of iterations to converge. And that's going to be defining the overall performance of the solver. So we are interested in for the stabilizing algorithm, and that's going to be the major algorithmic challenge. And how can this be plugged into ML pipelines? So what's quite common nowadays for ensuring the feasibility of the machine learning output is that you have some projection layer in the very end of the machine learning architecture. And projection is essentially an optimization problem. And if you want to accelerate the training procedure, you might want to accelerate the solving that projection problem in the very end. And for this batch optimization solver, we believe that can be used for the machine learning pipelines. So yeah, this concludes my talk today. So today I have I think I gave some high-level overview of what do we mean by pivoting free integer point method, and how can we utilize this emerging GPU-based sparse linear algebra and the matrix factorization techniques, and how can they be used within the optimization solver. So nowadays, if you think of if people talk about the GPU solver, they most of the times in the factorization-free method. But one of the messages that I want to deliver today is that with the second order method and the direct linear algebra-based method, you can actually do the GPU implementation, and they can very effectively apply to large-scale optimization problems. And we have talked about the lifted KKT and the hybrid KKT system, but this is more of our method that for demonstration and see if this actually works. And then in the future, we plan to further explore different options for implementing this algorithm, and then we can hopefully close the gap between the CPU server and the GPU server in terms of the reliability of the convergence. Okay, so this is the publication, the related publication, and I'd be happy to take any questions.
Thank you, Sungho, for the great talk. So feel free to unmute yourself if you have questions for Sungho. And also for the offline audience, if there is also. Okay, maybe I can start one, Sungho. So because you mentioned you are working many other sparse program, right? And you also mentioned some application on the Algebraic. So I'm wondering where this sparsity come from. Is it because of this connectivity among the different units?
Yeah, that's a really good question. I don't think I have the relevant slide today, but I'll just explain it words. So if you think about the transmission system, essentially it has the mesh-like structure. And in the problem formulation level, what happens is that you can associate each of the variable to specific physical component. That can be the generator, that can be the transmission lines, that can be the bus load. So they're not. If you look at the connectivity pattern, they're not directly connected unless they have some physical coupling there. So for example, if you look at the power flow equation, only the nodes that are in the both end of the arc is appearing. And if you look at the sparsity pattern, actually that physical system structure is preserved in the constrained Jacobian structure and the Lagrangian Hessian. And because of that physical sparse coupling, we have the if you look at the system level at the problem level, you actually see some of the sparsity patterns. And that applies to many of the physical systems. So for example, if you think about the gas pipeline infrastructure, it has a similar pattern. And if you discretize the partial differential equations over the finite difference or the finite element mesh, you only are coupled directly. Of course, at the solution level, everything is coupled together. But if you look at the algebraic coupling structure at the problem level, well, it's only coupled with the neighboring node. So from there, the sparsity pattern arises.
Yeah, that's clear. Yeah. Okay, Mohammed, please go ahead.
Thanks for your fantastic presentation. It was very nice. I have a quick question. I was wondering because in various applications we are dealing with like semi-definite programming and symmetric matrices. Correct me if I'm wrong. I guess what you have presented was mainly on the vectors rather than matrices, but it can be readily extended to the case of STPs. My concern, my only vague point is that how to ensure the loner order, the semi-definite semi-definite inequality. So is it the case? So can you have it in your paradigm, like in generating GPU-based optimization?
Yeah, so that's a great question. Like we don't do that much of the semi-definite program on our end, so like my insight might be slightly limited. But there are people who have been developing the conic optimizing solver. There's the solver that's called Clarabelle, and that has been focusing like as far as I know, they haven't looked into the semi-definite programming yet, but like I might be wrong on this, so you might want to check their work. But if you are doing the interpoint method for semi-definite programming, but as long as you can form this like linear system that needs to be solved within the interpoint method, then you can still apply this QDSS solver. And because for the semi-definite programs, you need to deal with these matrix variables. Potentially there can be more room for the parallelization, but of course I don't have the first-hand experience of implementing that, so like there might be some different set of challenges, but my expectation there is that because that's another linear system to solve, and then like as long as you can express them by using this positive semi-definite or the quasi-definite system representation, they can be exerted pretty effectively on the GPU. So for these particular algorithms, many of the challenges were actually coming from the non-convex nature of the problem. So if you apply this to the convex optimization problem or like things like LPs or QP, they're typically easier way to enable this structure. So with a very small regularization, you can ensure the positive symmetric quasi-definiteness in the metrics, and in that way you can use the GPU solver pretty effectively. And if you are reducing that down to the normal equation, which is kind of the standard method in the linear optimization, it can also ensure that they can be factorized on the GPU. So many of the challenges that I mentioned today applies to the non-convex optimization problems. So for the semi-definite programs for the interpoint method, I would assume that that there will be less of the challenge in terms of porting the numerical linear algebra on the GPU.
Thanks a lot. Thank you.
Thank you.
Any more questions from the audience? Koti, please go ahead.
Yeah, I'll ask one. Good to see you, Sungho. Short question about, well, I guess two questions. One a bit more technical, one a bit more general. A couple slides after this, you mentioned something about has sufficient inertial condition or something along those lines. I think it had to do with the here. If the system has correct inertia. So what exactly does that mean? Does that relate to any of the constraint qualifications that I normally hear about, or is that something else in there?
Yeah, so that's a great question. So I was a little bit like not giving the full detail here.
Of course,
by correct inertia is that in order to ensure that your step that is computed based on this, you want to ensure that goes into the nice direction. And for the non-convex problem, that's not always the case. So if you think about the unconstrained optimization case, you do the Hessian modification to ensure that your modified Hessian is positive definite. In that way, you can ensure that at least by solving that problem, you can improve the objective function. And then for the constraint optimization space, that's slightly different, but the idea is quite similar. So you need to have the correct inertia. Like this means that if you count the number of positive, negative, and the zero eigenvalue, there needs to be some of the condition that needs to be satisfied. And then with that, like you can ensure that the descent direction with respect to the merit function, which is combination of the constraint violation and the objective function. So that condition needs to be satisfied, and in particular, the number of positive eigenvalue need to match with the primal block, the size of the primal block, and the negative eigenvalue should match with the dual block. So the negative eigenvalue should match with the number of constraint, and there needs to be 0 eigenvalue, and that's kind of the requirement. And until you satisfy that condition, typically the nonlinear optimization solver apply this primal and the dual regularization. So what I mean by the symmetric passive definite even only if the system has the correct inertia is that you need to apply that regularization anyway. And if you're implementing the CPU solver, you're going to be applying that regularization at this level. But with the same degree of the regularization, as long as you have the regularization implemented, you have this system symmetric passive definite, meaning that you don't need to force the passive definiteness by using this primal regularization. If you choose large enough value for delta P, you can always make this passive definite, but that's not something that we want. We want to minimally apply the regularization and then still ensure the passive definiteness. And what I mean by that is that you don't need to you don't need to do the extra regularization to force this passive definite condition.
Okay, very clear, very clear. And then a more general question. So if I want to start implementing some of this on some MPC, could guess that I would want to do I have to move everything to Julia? Or do you have anything in Python that I can?
Yeah. That's a good question. Like this is kind of the main pain point, and then this is to some extent this is limiting the adoption by the practitioners. And to answer the question, at this point, if you, for example, insist on using Kasadi and then just use the solver, that's possible. And there's some of the proof of concept like implementation of interfacing this to Kasadi, but you need to pay quite high performance penalty, and that's because like I briefly mentioned that in the during the presentation, you want to move everything over to the GPU to be fully utilizing the GPU computing resources. And if you use the Kasadi will evaluate the model function and derivatives on the CPU. Like Kasadi is pretty efficient implementation, but the penalty that you need to pay is the back and forth between the CPU memory and the GPU memory. And then that means even if individually CPU implementation and GPU implementation is effective, then the overall performance is going to be pretty bad. So if you want to fully utilize the capabilities, you need to ensure that you can do the AD on the GPU. If Kasadi has that implementation at some point, probably we can have a better, easier implementation path. But right now, if you want to utilize this capability, you need to move things over to the GPU, to Julia.
To Julia, to use Jump or something like that to do it, or
Jump is. So we have a somewhat experimental interface to Jump, but also Jump. Yeah, essentially that's a like more generic algebraic modeling package. But our implementation is in examodels.jl. I briefly talked about and then this kind of designed in such a way that we can ensure the GPU compatibility. But for doing this, supporting this for generic algebraic modeling system is still a big challenge, and that's because you can think about the evil model where you have like different pattern in each of the constraint, and then like you cannot think about like writing the GPU kernel that applies the similar operation to each of the entry. So supporting the generic nonlinear optimization is quite difficult. So like we have designed some system that forces the user to provide the structure that is used for exploiting the parallelism. So that's what we did in examodels. So it could be the case that the GPU compatible nonlinear optimization may require some GPU specific algebraic modeling system.
But very clear.
But for the complex or the quadratic program, like those have the predefined like structure, and then for doing that, like GPU can still probably use, but for the nonlinear, like it's gonna be quite difficult.
I guess.
Okay, clear. Thank you.
We have some questions from the offline audience. So audience in the room, Vincent.
I was wondering about the relaxation of the equality constraints. If you could change like the strictness per variable, if there's some variables you care more about, does that still like give you the performance a decrease if you have one variable that's more strict? And also how the strictness impacts the robustness, because you lose accuracy, but how is the robustness if you have more or less accuracy?
Yeah, that's a good question. So far, we haven't tried to use the strategy that you have described. So we always use the uniform relaxation, meaning that we just relax all the constraints by some constant vector, and that was given by the solver tolerance. So by default, on the GPU, we use 10 to the minus 4, but for the CPU, that's 10 to the minus 8, and you have seen that like that can lead to some numerical instability. So using the different value for this, like based on some scaling information, I think that might be a good idea, but we haven't yet had a chance to explore that direction. And the consequences of using different tau value, and actually this is related to the numerical behavior of the solver. And if you use a tight value of tau, what happens is that some of your variable will be very close to the boundary, and that term will appear in the log barrier function in the interpolating method, and then this term will have like higher values or the lower values, actually mostly the higher value. And that means the system that you need to handle numerically will face more numerical the ill conditioning issue. And that's actually what we are observing from the benchmark result. You actually fail in some of the instances, and then generally the iteration count becomes higher. So right now, this is kind of the this is where the limitation of the algorithm is right now coming from. You need to do this relaxation, and if you set this parameter to be very slow or very small, that will cause the ill conditioning in the metrics, and that can lead to some of the behavior, some of the limited behavior of the solver reliability. Did that answer your question?
Yeah, thank you.
Yep.
Okay. But given the time, I suggest we conclude similar. And let's thank Sungho again for his great talk and very interesting research. And Sungho, I say, let's keep in touch.
Yep. Let's keep in touch. Yeah. Thanks for all the questions. I think I enjoyed giving the talk at TU Delft today. So yeah, I'd be happy to like meet some of you in the future in the conferences. Right.
Yes. Let's see you.
Thanks,
Bye.